Hello everyone. In this video, we will learn about a tool that we will use throughout this course for counting and different topics. It's called trees, and in particular in this video, we will cover one special case of trees that can be used for counting. Okay, let me start with saying few things about what is a tree and some terminology for the trees. So trees are types of graphs, meaning that they are formed by some points and some lines which connect the points, and the graphs we are interested in, the trees, these don't have a cycle. It means that from any point to another point, there's only one path to move on. Okay? There are some terminology. For example, the points are called nodes. Even the points itself, sometimes vertices. The lines are called branches, or sometimes they call edges. They are called edges. So the trees that we are working with, there's an assumption that they grow in one direction, and we usually grow them from the left to the right. In other words, the graphs are, for us, directed graphs, directed direction. But we don't put any direction. This is just something that, convention that we follow. And since everything is grow in one direction, there will be one node that everything comes out of it, and that is called the root. From the root, if you continue going through the edges, you will end up to at the end, some points. Those points, the very last point on the other side of the tree, these are called terminal points or vertices or nodes. Well, you will see that in some cases we will label edges. Sometimes we will label the points themselves, but there is no rule that you need to see all the time. And in particular, what we are going to cover today, there won't be any labeling for edges. Let me then start showing you how one can use a tree to solve a counting problem. We will do through an example, and then we will see what are the points there. Okay. Find the number of different ways that a cashier can give 65 cents back to a customer in change using three types of coins: quarters, dimes, and nickels. Okay, so the way we think about this problem is that, okay, this cashier had this box of coins, and she wants to give back the cash to the customer. So first, she starts with a quarter box. How many quarters I can give to this customer? Well, let's say at most I can give 2, or I can give 1 quarter, or I can give a non-quarter actually. Then I look at the 2 quarters. If I give 2 quarters, as a result, I have already given 50 cents. So there will be 2 options left for me. If I go to the next box, which is the box for dimes, I can give at most I can give 1 dime or no dime. But if I have given 1/4, depending on the choice that I had made in the previous box, the story will be different. If I have given 1/4, 25 cents already given, so I have 40 cents to cover. So I will go either 4 dimes or 3 dimes or 2 dimes, 1 dime, or none. So I'm done with that case. If we give no quarters, then the story would be a little bit different, yes? So at most I can give 6 times there, 5, and go down like that, 4, and 3, 2, and 1, and there's one more 0 time. Yeah. Now if you have all these options there, the next thing would be just to go to the third box, which will be the box for the nickels. Yes, so based on whatever you have given in the first step and the second step, so from the first box or from from the second box, there will be only one choice there, because we're already given, for example, in this case, 2/4, that's 50 cents, then 1 dime, that's 60. The remaining would be 1 nickel. Then if you have given 2/4, no dime, the remaining will be 3 nickels. 1/4, 2 dimes, this will give us well, what is that? That's no nickels. 2 nickels, and you go 4, and then 5, and then no, I don't like this. If I give him 1/4, 3 dimes, I need to give 2. 1/4, 3 dimes, that's 55. That's, yes, this is 2. This is 4, but the next one I need to give 6 nickels. 1/4, 25, 135, then 65, then 8 nickels. And for this one, no quarter is given. No quarter is given, 6 dime, so that will give you 60. So 1 nickel would be the remaining, 3 nickels, 5 nickels, 7, and 9, 11, and 13. So the numbers or the things that I'm putting there just for me to generate this tree, the tree of all possibilities for this change return, yes? Now, each path from the root to one of these terminal points gives us one of these scenarios to complete this task. In other words, if I move from this, and there's only one way to go from the root to any terminal path, this way, it means that 2/4, 1 dime, 1 nickel. The other one means, okay, let me, don't put the line, just don't make the graph extended there. So 2/4, 0 dimes, and 3 nickels. And this goes on. And each one of these terminal points gives me one way to complete this task. So if I count the number of end points, I have counted all the possible ways to give this 65 cents back to the customer, yes? So let me count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There are 14 ways, that's the answer, to return that 65 cents. And while this kind of trees, when are useful, so this is the point. Whenever the task is formed from a sequence of other tasks, then which changing one, which a choice in one can change the next ones, then we use this type of trees. So in this case, remember, choosing quarters were first task to do, then dimes came the next, then nickels came the third. So there's the sequence. So first choose the number of quarters, the number of dimes and number of nickels. Okay. The second remark here is that we already saw there is no labeling here. So each path from the root to a terminal point or terminal node gives us a way to complete the task. So the different, as a result, the number of endpoints gives us the number of ways we can do this task. Okay. So that's the kind of trees we want to use, and you saw already in one example how does that work. Let me move to another example and see how we can do this kind of trees and count more cases. There is a game, we are tossing a coin, and we will follow these three rules to determine when to stop. When there are three heads, when there are two consecutive tails, or when the coin is tossed 4 times. So as you notice, there is a sequence of actions to be taken. First toss, second toss, and up to fourth, yes? So let's start with the first one. So I toss the coin. What I get is either head, or maybe I should do a little bit higher there. So a head or a tail. So I will put head, tail, just to determine the case. So there's nothing, none of the rules stop us from doing the second one. So I will do a little bit not symmetric. So edge and tail. So I toss the second one, it gets either head or tail, and then I do another time, get head or tail. Yes. So this is the second toss. But right away, you notice that the second rule tells me that if there are two consecutive tails, you have to stop. And you notice this last path or the last branch ends up with 2 tails, 1 and 2. Now, the others can grow out still. There's a third toss, so I can get either head or tail. I can get head or tail, and I can get in the third toss head or tail. Doesn't matter what is the previous step, we either have a toss or not, so it will be head or tail. Okay, Then, well, look at this condition 1. It says whenever there are 3 heads, you have to stop. This path represents 3 head coming right one after the other one. And also this one, there are 2 heads, consecutive tails. So I have to stop that branch as well. Okay? Then the rest you can toss again. So this will be either head or tail, a head or tail, head or tail, and the last head and tail, and done. The last condition says that don't toss more than 4 times, no matter what are the results. So that means that any of these last ones will be a terminal node or vertex as well. Now, the number of ways we want to. So you can see that, for example, the first branch, so the first path from the root, the first end point or terminal point will give me H, H, H. The second one is H, H, T, H, and then H, H, T, T, and this continues, yes? Each terminal point gives you one scenario. Now I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. There are 11 ways that this coin toss can be done. There will be another type of trees that we can use for counting. Those are labeled ones, and you will see that we will use more of those kinds, and they're going to be called counting trees.